at the conclusion of our talk yesterday, when we reminded you that at coordinate covalent bond sites beside the sigma bond, which is always present at a bond site, there are a couple of exceptions to that regarding coordination chemistry. We shall not consider the exceptions. So from our standpoint, at each bond site, there is always one and only one sigma bond. But as with covalent bond sites for molecules, for transition metal complexes, it's also often the case that pi bonds are present. How do the pi bonds form? The model we use is to imagine that a valence d electron rich coordinated transition metal atom or ion can use these d electrons, or d electron density, which of course reside in d orbitals. We've already noted that d orbitals can make pi bonds, and function as a Lewis base in making the pi bonds, and share this electron density with empty valence orbitals on the ligand, which are capable of making pi overlap, making pi bonds. As a specific reference, I told you to look at the molecular orbital considerations regarding carbon monoxide that are found in chapter 25 on molecular orbital theory, because we've already argued that the stability of complexes like nickel tetracarbonyl, where the metal is in an unusually low oxidation state, or this anionic complex of cobalt, or this anionic complex of iron, are attributable to pi bonds and pi bond strength rather than sigma bonds. Take a look at that if you've not yet done so. And to give you a better idea about the nature of these pi bonds and their strength, for these complexes which we considered in past conversation, there were a couple of other complexes, but I didn't write them all up here. In which of these complexes should you expect to find the strongest pi bond interaction between the coordinated metal atom or ion and the ligands, the transition metal chemists for the Lewis bases, which interact with the Lewis acid transition metal atom or ion to make the sigma bonds? Now watch out for the language, don't stumble on it. Because again, in making the pi bonds, the metal atom or ion supplies the electron density to make the pi bonds. So in that regard, the metal behaves as the Lewis base to make the pi bonds. Which one? What properties would you expect are requisite for a coordinated metal atom or ion to be a pi bonder? Well, if it's using d electrons, then it's got the metal atom or ion which has got the greatest abundance of d electrons on that basis will likely be the better pi bonder. But for these complexes with the metals in unusually low oxidation states, the metals are invariably showing a full complement of valence d electrons, 10 of them. Any other considerations which might relate to the pi bonding ability of a metal atom or ion? In this complex labeled 1 for reference, what's the oxidation state of the metal? In this complex labeled 2 for reference, what's the oxidation state of cobalt? -1. And in this iron complex, -2. Well, tell me, from which of these species, from a Coulombic standpoint, would you expect the greater pi bonding ability? From which of these species, from a Coulombic standpoint, would you expect more ready sharing of d electron density with empty valence orbitals on the ligand? 0 oxidation state, coordinated metal, -1 oxidation state, coordinated metal, -2 oxidation state, coordinated metal. Well, if no other factors mattered, regardless of pi bonding at a coordinate covalent bond site, if you're looking at 3 different Bronsted bases, 0 charge, -1 charge, -2 charge, if no other factors mattered, which of these will be the better Bronsted base? -2. Same thing here. So we shall expect the stronger pi bonding, as far as the metal is concerned, to be observed in this complex. Now, as in a Bronsted-Lowry acid-base reaction, you can't talk about the strength of a Bronsted acid all by itself. That has no meaning. You have to also focus on the ability of the H+ acceptor, the Bronsted base. Same thing here. To talk about the pi bonding ability of a metal atom or ion in a meaningful fashion obligates you to talk about the ligand with which you are imagining the metal atom or ion to engage in pi bond formation. Well, we're only looking at 2 different types of ligands here: carbon monoxide and NO+. These are formal charges. This is an actual charge. This is a cation. This is a molecule. So based on the combined electronegativity of the component atoms and based on charge, which of these things do you think would more effectively attract the electron density, or electron density in general? This thing is plus. And the combined electronegativity of these 2 atoms exceeds the combined electronegativity of these 2 atoms, because nitrogen is more electronegative than oxygen. So bet on this as the best pi bonding ligand, or the better pi bonding ligand, since we're only comparing 2. So, here it is. Let's move along now to chapter 24 on a formal basis. I've written here, TM coordination chemistry continued, exclam, because all this stuff that we did at the tail end of chapter 23, as we've already noted, has provided foundation for jumping into chapter 24. Because everything we talked about here is about transition metal coordination chemistry. All right, a couple of questions start the chapter. The zinc family. Even though the periodic table shows you the family of atoms where zinc is the topmost member, not really classified as transition metals, even though they're in one of these short vertical columns. Why not? Based on chemical behavior, what distinguishes a transition metal from a non-transition metal? Well, it has to do with d orbitals. If you're going to write a working definition of a transition metal versus a non-transition metal, what would you say? Perhaps you recall when we started talking about transition metals, we said it's standard practice in general chemistry to postpone conversation about transition metal chemistry till the end of the line, because it's more sophisticated, it's more complex, than the chemistry of non-transition metals. Why so? Because many transition metals have the ability in their chemistry to develop 2 or more stable oxidation states. You rarely find that for non-transition metals, like family 1A metals. They lose 1 electron per atom as they react, and there's no other chemistry shown by these metals. The family 2A metals, they lose 2 electrons per atom when they react, and that's it. But transition metals often can develop different stable oxidation states. Manganese, for example, shows a stable +2 oxidation state, a stable +4 oxidation state, a stable +6 oxidation state, a stable +7 oxidation state, and a somewhat stable +3 oxidation state. A lot of different kind of chemistry going on there. Valence configuration for manganese by itself is 3d5,4s2. 7 valence electrons. So, unlike the non-transition metals, where the most common chemistry is to lose all the valence electrons and develop the corresponding cation species with a charge equal to the number of valence electrons you lost, not with transition metals. All kinds of different oxidation states are developable. Well then, why shall we not classify zinc or cadmium or mercury as transition metals? Did you learn, I'm curious, in 2045, from a nomenclature standpoint, if nothing else, what's the only positive oxidation state ever developed by zinc in its chemistry? +2, that's it. How about cadmium? Maybe you didn't talk about cadmium. But like zinc, cadmium only develops a +2 oxidation state, that's it. Now mercury, because of the ability of mercury atoms to bond with each other and form the unusual mercurous ion, which is Hg sub 2+. Mercury atoms develop most commonly +2 oxidation state, like zinc and cadmium, but sometimes +1. But never any oxidation state exceeding +2. Which means the valence d electrons of zinc and cadmium and mercury are practically speaking not part of their chemistry, unlike transition metals. All right, 24.2. 24.2 says, note that in studying the chemistry of the transition metals, you find that the first row transition metals, which starts with scandium and winds up with copper, compared to the second and third row transition metals, second row zirconium through silver, and then hafnium through gold, the second and third row transition metals, from periods 5 and 6 respectively, more readily develop positive oxidation states than the first row, the fourth period transition metals. Well, I hope that translates to meaning to you that this means the second and third row transition metals must have lower ionization energies. They must be easier to ionize if they more readily develop positive oxidation states. Why is that? What'd you find out about trends in ionization energies? For the atoms in a family, how do ionization energies compare trend-wise as you go from top to bottom? Ionization energies stay the same, get bigger, or get smaller? What do they do? Do the ionization energies get smaller, larger, or stay the same as you go from top to bottom? They get smaller. Atoms become progressively easier to ionize, even though, as you go from top to bottom, you're looking at a much, much larger number of protons in the nucleus as you go from period to period. But we reminded ourselves at the start of the conversation in chapter 23. Z effective is what matters, not Z itself. Z is atomic number. I mean, if potassium is easier to ionize than sodium, then Z effective for the 3s1 valence electron of sodium has got to be a larger effective nuclear attraction than Z effective for the 4s valence electron of potassium, independent of 19 total protons for K versus 11 total protons for Na. Well, same thing for the transition metals. As the atoms get larger, they become easier to ionize. And again, we're looking at Coulomb's law, that d squared term in the denominator is the controlling factor. Because as you make an atom larger, the interaction or attraction between Z effective and outer lying electron falls off by the increase in size squared. But when we get to period 5 and 6, the second and third row transition metal atoms, we find that tendency to form positive oxidation states is about the same. If you look at ionization energy, you'll find out they're about the same for atoms in the same family. If you look at ionization energies, you find out they're about the same. In some cases, the fifth period atoms are larger, somewhat, than the sixth period atoms. How about that? You got a hell of a lot more electrons in the electron cloud for the sixth period atoms. I mean, look at, for example, gold versus silver. 79 protons, 79 electrons for a gold atom versus 47 and 47 for the silver atom. Yet the gold atom and the silver atom about the same size. Show about the same ionization energies. How can this be? We talked about this, but not in great detail, and again at the start of chapter 23. When we talked about shielding and penetration effects. From a total electron configuration standpoint, what's the major difference between the period 6 transition metals and the in-family period 5 transition metals? What's the major difference? F orbitals and F electrons. The period 4 atoms got F orbitals, but no F electrons. Period 5 atoms got F orbitals, but no F electrons. Ha-ha! But when you get to period 6, now you've got F orbitals which are filled. Well then, how does that impact size? How does that impact ionization energy? Are F electrons good shielders? No. Lousy shielders. So imagine, for example, a gold atom. What's the valence configuration for a gold atom? Valence configuration. Well, it's in the copper family, isn't it? You remember that copper shows an electron configuration, valence electron configuration, which is developed somewhat contrary to that which is predicted by Aufbau? Aufbau predicts for copper D9S2, but copper is actually D10S1. So is silver, so is gold. They're all D10S1 atoms. Three D4S, 4D5S, 5D6S. But this 6s electron of gold has an ionization energy requirement which is about the same as the 5s electron of silver. Isn't that unusual? Since in the nucleus of gold you got 79 total protons versus 47 total protons in the nucleus of silver. Well, the answer to the question lies in the main, in realizing these F electrons and how they behave. They're lousy shielders. They're lousy penetrators. Upshot, this 6s electron of gold, remember those radial probability pictures? When that 6s electron of gold penetrates toward the nucleus of gold, which it does rather effectively because this 4f filled sublevel does not shield that 6s electron effectively at all. That 6s electron is poking toward a nucleus which has got one hell of a bunch of protons in it. Upshot, Z effective is considerable. Winds up being about the same as Z effective exerted on the 5s valence electron of silver. It must be if these atoms are about the same size and have about the same set of ionization energies for valence electrons. All right, language. Coordination complex. We really already know what these things are. They're formed by Lewis acid, Lewis base reactions. In forming the sigma bond, the transition metal atom or ion behaves as the Lewis acid by supplying empty valence orbitals, and the ligand, the transition metal chemist's name for a Lewis base, a species capable of making a sigma bond, at least one, supplies the electron pair to make the sigma coordinate covalent bond. But, as we have already discussed, to try to make this aspect of coordination chemistry more palatable to you as we plow further through chapter 24, pi bonding at a coordinate covalent bond site, or bond sites, in a transition metal complex, arises from interaction between transition metal valence d electrons, where in this respect, in making the pi bond, the transition metal is behaving as the Lewis base because it's supplying the electron density to make the pi bond. And empty, you've already seen this before. I'll put quotes on it to remind you that this means that. Pi bonding valence orbitals on the ligand. Well, in this case, then, the ligand is supplying the empty valence orbital to make the pi interaction. And so, in this respect, pi bond formation, the ligand is, at least the model we use, is behaving as the Lewis acid. So this leads to role reversal, right? Making the sigma bond, the Tm atom or ion, Lewis acid, the ligand, the Lewis base, because it supplies the electron pair to make the sigma bond. When you make the pi bond, role reversal. Now the ligand supplies the empty valence orbital, behaves as the Lewis acid. And the metal atom or ion supplies the electron density to make the pi bond interaction. When making the pi bond, the metal behaves as the Lewis base. First coordination sphere. Look at nickel tetracarbonyl. The 4 carbon monoxide ligand molecules which are part of the composition of that complex are said to be in the first coordination sphere. In the cobalt complex, the 4 coordinated carbon monoxide molecules are in the first coordination sphere. In the iron complex, the 3 carbon monoxide molecules and the NO plus ligand, this cationic ligand, are in the first coordination sphere. That's just a reference to the ligands which are in fact bound directly to the metal atom or ion. The coordinated ligands. Now, I expect that when I rewrite these notes, which I'm working on now, but it's a very, very long and arduous task, I'll probably leave this term out. Because transition metal chemists have found that in addition to the actual coordinated ligands, the behavior of a transition metal complex can be affected by other ligands in the same chemical system, but ligands which are not coordinated. They're swimming around in the solution which contains the transition metal complex. Such ligands are said to be in the second coordination sphere. And if you throw size in there, you might even get them to be in the third coordination sphere. But we pay attention exclusively to the chemistry of the complex itself and don't pay any attention to the effect, chemical effect exerted on the complex by ligands which may be in the chemical system but which are not coordinated, other than from an equilibrium standpoint. We'll of course pay attention to that. But beyond that, we don't care about the second coordination sphere or even third coordination sphere, etc. language. So I'll put this on here if for no other reason. It's stated in the notes. Coordination number, a simple concept. If you look, for example, at a metal lattice, just an elemental metal, you've already learned about coordination number. And I know in Chemistry 2045, all of you had some conversation offered you about lattices of metallic elements. And you learn language like simple cubic and body-centered cubic and face-centered cubic, which is the same thing as cubic closest packed. Those terms ring a bell. You remember what the coordination number is for a metal atom in a simple cubic lattice? Body-centered cubic lattice. Cubic closest packed lattice, same as face-centered cubic. I'm curious if you remember that. 6, 8, 12. Cubic closest packed. Coordination number is 12. What's that mean? That means if you look at an atom of a metal in a cubic closest packed lattice, the metal atom you look at will be in contact with 12 other metal atoms by metallic bonds connected to these 12 other metal atoms. So coordination number for transition metal chemistry is just a count. It's a number of sigma bonds. It is the number of sigma bonds between coordinated transition metal and the ligands. Now, don't take this to mean, coordination number, the number of ligands itself. Because in just a moment we're going to start to talk about ligands and their nature in a more detailed fashion and recognize that certain ligands have the capacity per ligand to make more than one sigma bond. And if you've started to look at bonus quiz 3, you'd already have an idea what I'm talking about. So, we're talking about the number of sigma bonds between coordinated transition metal and the ligands in the first coordination sphere. Most common coordination number for transition metal complexes is 6, which corresponds in the main to octahedral geometry for the complex. Now, to move along, we'll talk now in brief about what can be argued as the origin of coordination chemistry. It's really more broad scope than that. It's argued as the work and results of Alfred Werner in the late 1800s. This is argued as the origin of inorganic chemistry as a separate chemical discipline. Way back when? Way back when? That's about late 1800s. Practically speaking, there were only two chemical disciplines then: organic and physical. That was it. Well, Alfred Werner is more or less given credit for being the father of inorganic chemistry, putting inorganic chemistry on the map by getting chemists to realize there's a whole lot of interesting stuff that can be learned from a chemist's standpoint about materials which are not organic in nature. Like Werner's quote-unquote discovery of the coordinate covalent bond for transition metal complexes. I say quote-unquote because I don't know that Werner actually recognized what the heck a coordinate covalent bond is like. But he did recognize that something was novel and unusual about the formation of bonds that took place when transition metal atoms and ions reacted with certain molecules. Let's take a look at a case. Cobalt-3 chloride, a simple salt, an ionic compound mainly. Cobalt in the +3 oxidation state. Pure stuff dissolved in water. That's it. A simple binary ionic compound dissolved in water. Now, why Werner did this, I don't know. There might be some account of this in the papers of his, which are still on record in libraries and the like. But his observations were really interesting. Cobalt-3 chloride is dissolved in water, and out starts to bubble oxygen. Redox chemistry. Where's the oxygen coming from? Surely you're not going to tell me that the oxygen is produced by oxidizing the little o in cobalt, making it a big O to turn it into an oxygen atom. You're going to tell me that, are you? Good. Comes from the water molecule. So, after seeing this, Werner said, well, I wonder what the hell's happened to this cobalt-3 chloride. To find it out, to my knowledge, he evaporated the solution to dryness to get a solid, and on analysis of the solid, found out that it had a composition corresponding to this formula. Cobalt-2 chloride, and per mole of cobalt-2 chloride, 6 moles of water. Solid. He says, what? Water by itself is a liquid material. Yet in this stable material, which is a solid, water is part and parcel of the composition of this solid. So he starts to say, well, something must be affecting the nature of water, causing it to be stable as a solid component of this material. But what about this redox chemistry? Well, he does another experiment. He goes back and gets some more cobalt-3 chloride. This time he doesn't dissolve it in straight water. He dissolves it in 6 molar ammonia solution. Now, in 6 molar ammonia solution, the main component is still water. But when he dissolves this cobalt-3 chloride in 6 molar ammonia solution, no oxygen liberation, no redox reaction. So again, to find out what has happened to cobalt, when the cobalt-3 chloride was this time dissolved in the ammonia solution, he evaporates the solution to dryness and gets a material which analyzes to give this composition. What? Ammonia molecules. Ammonia molecules by themselves, under normal laboratory conditions, are what phase? Gas. But it is solid. This is really neat stuff. By this kind of chemistry, whatever it is, Here I get water to be solid state. Here I get ammonia molecule to be solid state, even though by itself the stuff is gas. And why no redox here? Why in this case, where water is the principal component of the system, am I not getting oxygen to be oxidized? What's going on? He didn't know. But I'll bet he had some good ideas. So I'll write these three formulas on the board. Because for each of these chemical systems, beside cobalt in the +3 oxidation state, you've got chloride ion contained in each chemical system, water molecules contained in each chemical system, and the ammonia molecule contained in the second chemical system, but not the first. Model. What's this a model of? What's it look like? If I asked you to describe this, what would you tell me this thing looks like? You seen something like this before? Well, what's it look like? Dempster dumpster? Dinosaur? Pair of shoes? What the hell does this thing look like? Huh? A what? A hydrated molecule. What here looks like water? He said it looks like a hydrated molecule. These are water molecules? Guess what? For the first experiment, these things do represent water molecules. Okay. But I want to know more. What shape am I looking at? An octahedral shape. Good. So, if it's true, I mean, given that it is true, pardon me, for experiment number 1, which species seems to be capable of behaving as a Lewis base more strongly toward cobalt in the +3 oxidation state? Chloride ion or water? Which of these seems to have the capability of interacting more strongly with cobalt in the +3 oxidation state? Water or chloride ion? Water. In the first experiment, we're starting with cobalt in contact with chloride ions, nothing else. We dissolve this stuff in water. And out comes oxygen. And cobalt is getting reduced from +3 oxidation state to +2 oxidation state. Does that not scream at you that in the first experiment, water molecules and cobalt in the +3 oxidation state must be making contact with each other? Yeah. So, we conclude that in the first experiment, the water molecules shove the chloride ions out of the way because they interact more strongly with cobalt-3, as indicated by the results of this experiment. Now clearly in the final material, since cobalt is still a positive ion, you've got to have some negative ions in the lattice. But look at this formula. Okay. Tell me, when you look at this formula, and you consider as a consequence of the conversation we're having, bond interactions sigma bond interactions between water molecules and or chloride ions. What do you think is connected to cobalt-2 in this compound? This is the way Werner wrote the formula, so I wrote it like Werner wrote it. What do you think is connected in contact with cobalt-2 in this stuff? You think it's chloride ions, water molecules, both? What's your bet? Did we not conclude as a consequence of the first experiment that water molecules are showing a stronger ability to interact with cobalt-3 than chloride? Well, here's our model. If we take the center of this model to be a representative of cobalt-2, then, as was earlier suggested, what are these white spheres simulating? Water molecules. Because what we now know regarding this first experiment is that cobalt is complexed by water molecules to make this thing, which is octahedral. And the chloride ions, that's not a chlorine molecule. Those are two chloride ions which are connected to this complex because of Coulombic attraction. All right? Now let's go to the second experiment. The only difference relative to the first experiment is that in the second experiment, ammonia molecules are also present. Tell me, which materials seem to form stronger bonds with cobalt? Water molecules or ammonia molecules? When we evaporate the solution from the second experiment, are we getting anything with water in it? No. So if I'm going to write the formula for the complex, the cobalt complex resulting from the second experiment, how would you write the formula? Would you bet this is the formula? Would you bet that for our model regarding the outcome of the second experiment that the white spheres are now representing ammonia molecules? But doggone it, water molecules are still the principal component of system number 2, experiment number 2. Why no redox? Because in order to get redox, you've got to get contact between cobalt in the +3 oxidation state and water molecules. Water molecule. Can't get there. The ammonia molecules have got this this cobalt-3 ion protected. How about that? And clearly, the outcome of the second experiment is to realize that ammonia molecules are capable of forming even stronger bonds with cobalt-3 compared to water. If it weren't so, we'd get the same result as the first experiment. Interesting, isn't it? Now let's have some more fun. A task which should be simple. Write the Lewis structures for these things right now. And remember, I don't use dots. I don't give a damn what the textbooks prefer. Ammonia, water, chloride ion. Four non-bonding pairs, plus a negative charge. Two non-bonding pairs, one non-bonding pair. Does it appear that the ability of a Lewis base to behave as such, or if you prefer, strength of a Lewis base, depends on the number of non-bonding pairs? Does it appear that the coordinate covalent bond forming ability of a Lewis base depends on number of non-bonding pairs? It does. But how? Chloride ion, four non-bonding pairs, regarding interaction with cobalt-3, has shown itself to be the weakest ligand. Ammonia with only one non-bonding pair, the strongest ligand. When we get further into this, we're going to find out that these bond formation interactions with a transition metal atom or ion are in one respect very different from interactions with H+. Yet for these three species, the interaction with H+ winds up being the same. This is the best H+ grabber of these three. It's also the best cobalt-3 grabber of these three. But just for fun, let's put that metal in the mix. Now who's going to win the game? Chloride ion is going to win the game, hands down. Water molecule doesn't even get in the game. It's going to fight with ammonia and chloride ion in competition for silver ion. We've already done this in chapter 19. Again, you can't really talk successfully about the strength of a Lewis base to behave as such unless at the same time you also pay attention to the metal atom or ion, the Lewis acid with which the Lewis base is interacting. Interesting. So, what Werner discovered, even though I doubt that he knew it, probably had some ideas about it, is the formation of the coordinate covalent bond. The ammonia molecules toward cobalt-3 were best. They surrounded cobalt-3 and protected cobalt-3 in experiment number 2. Didn't let the water molecules get in there and stir up this redox reaction. But, since this relates directly to stuff we did in chapter 22, I'll ask again. In this experiment, where we got oxygen, what do you think happened to system pH as this reaction ran? You think the system pH stayed the same? Went down or went up? Any idea? You got table 2 handy? Chapter 22, table 2. That list of half reactions. Take a look at it. We're looking at a redox reaction in which oxygen is an oxidation product. Look at table 2. You see any half reactions involving the production of oxygen? What happens to pH as oxygen is produced by oxidation of water? Because that's what got oxidized in that first experiment. What happens to pH as oxygen is produced by oxidation of water? What happens to pH? Does it go down, come up, stay the same? What does it do? Goes down, because in addition to producing oxygen, what else are you producing? Hydronium ions, you betcha. And now, let's get on with establishing some more fundamental coordination chemistry considerations. Types of ligands. We've already talked about 3 types of ligands here. Well, 3 ligands, pardon me, rather than 3 types of ligands. We reminded ourselves that the ability of these things to behave as ligands certainly depends upon the species with which these ligands are expected to interact. Cobalt-3, H+, ammonia wins. Put silver ion in the game, chloride ion wins. Tell me, when chloride ion beats the pants off ammonia in water in behaving as a Lewis base towards silver ion, do you think chloride ion wins the battle for silver ion because of sigma bond formation? H+, Ag+. Do you know a better sigma acceptor than H+? H+ is nothing but a bare nucleus with a positive charge. Does that sound like a rather substantial positive charge density? You betcha. Whichever species is capable of supplying, or pardon me, possessing the greater negative charge density is certainly the species which is going to interact most strongly with H+. And ammonia and water both beat chloride ion in this regard. Chloride ion's got a formal negative charge, but it's so damn big, its effective negative charge density is not much at all. But when we put silver ion in the game, which is also a plus species, now chloride ion wins. Well, if this is a much stronger sigma acceptor, not compared to this, but anything, do you think chloride ion winning the battle for silver ion has to do with sigma bond strength? Chloride ion loses in the battle for H+. Or you can't form anything but a sigma bond. H+ can't make anything but a sigma bond. And the ammonia molecule H+ bond formation interaction is the strongest compared to water molecule H+, which makes hydronium ion, or chloride ion H+, which will make you HCl. Do you think the extreme stability of this material depends on sigma bond strength between chloride ion and silver ion? No way. Well, if it ain't sigma bond strength, then what kind of bond strength must it be? Pi bond. You think silver ion can be a pi bonder? Has silver ion got a rather substantial complement of valence d electrons? How many valence d electrons does silver ion have? 10 of them, they're all there. When silver atom becomes silver ion, you do so by losing a 5s electron. You don't do anything to the 4d10 sublevel. You think silver ion's got a pretty small positive charge density? It's only +1, it's a big ion. How about chloride ion? Can chloride ion make pi bonds? Can chloride ion make pi bonds? If so, how? How can chloride ion make pi bonds? Is chloride ion not in fact derived from chlorine, which is an atomic member of period number 3? Can period number 3 atoms make pi bonds by acting as Lewis acids? Period 3 atoms. Can they make pi bonds by acting as Lewis acids? What kinds of valence orbitals do you have to make pi bonds?
D orbitals.
P or D? Not S. Does chloride ion have any empty valence orbitals as part of its valence environment, which are capable of pi bond interaction? What are these valence orbitals? 3D! Just like every period 3 atom. None of them have valence 3D electrons, but they all got valence 3D orbitals. All right, back to this stuff. Denticity. Just like the dentist. How many bites can a ligand take on a metal atom or ion? How many bites? How many sigma bonds can it make? That's what denticity is about. Water molecule. Oh, I erased it. Is a monodentate ligand. It's got 2 non-bonding pairs. But you know how this atom is hybridized? sp3. So what's the spatial directionality of these non-bonding pairs with respect to each other? Are they aiming at the same location in space? sp3 hybridized atom. So these 4 valence electron pairs for the water molecule, 2 of which are bonding, 2 of which are non-bonding, are at angles which are on the order of 109 degrees apart from each other. So if a water molecule floats over here and coordinates to my noggin, which is now a metal ion, the other non-bonding pairs aiming that way. So a water molecule can't make, with a given metal atom or ion, more than 1 coordinate covalent bond. Just like the ammonia molecule. Of course, that's obvious for ammonia molecule, because you only got 1 non-bonding pair. How about chloride ion? 4 non-bonding pairs. Can chloride ion make more than 1 sigma bond with silver ion? Hell no. If you're the silver ion over there, and I'm the chloride ion over here, I got 1 sigma bonding capable non-bonding pair looking at you, and the other ones are directed away from that bond site. Bidentate ligand. I'm going to now write a Lewis picture on the board. For what I believe to be the best known bidentate ligand. Its name is ethylene diamine. I don't care about its name. You can learn about that in organic class. But it's commonly abbreviated as EN. A, because it's so very common, and B, because its name is ethylene diamine. EN. Tell me, if I ask you to describe the geometry of this molecule, what will you say? How does it appear spatially? Do you see that on this nitrogen atom, it's got a non-bonding pair like on this nitrogen atom, which is why this thing is capable of behaving as a bidentate ligand. Bidentate. How many sigma bonds toward one metal ion can this thing make? 2. Now, just because I couldn't find any other colors, I'm using red things to simulate hydrogen atoms. These black plastic parts are simulating the carbon atoms, and the nitrogen atoms are simulating the nitrogen atoms for ethylene diamine. There's a model of ethylene diamine. All the skeletal atoms are sp3 hybridized. So we're looking at bond angles throughout the bond skeleton of this molecule, as well as the bonds to the peripheral hydrogen atoms. Bond angles are all about 109 degrees. Not quite, because you got non-bonding pair, bonding pair repulsion. At least not quite for the H and H bond angles. Because you got non-bonding pair, bonding pair repulsion, which exceeds bond pair repulsion. When at the covalent bond sites, you only got one bonding pair. This look like an acceptable model for ethylene diamine? Showing the zigzag skeletal structure because of sp3 hybridization. But you learned in 2045, I trust, that when the bond order at a covalent bond site is 1, a single bond only is connecting the connected atoms, that the atoms and species connected to the atoms at a single bond covalent bond site can rotate in directions opposite to each other in space without breaking the bond. It's called free rotation. As soon as you have any multiple bonding electron density at a covalent bond site, you lose this free rotation characteristic. But how does this free rotation characteristic allow something like ethylene diamine to be bidentate? Well, when I hold a molecule like this, you see this non-bonding pair aiming that way and this non-bonding pair aiming that way. But because of this free rotation along these coordinate covalent bond sites, look now. I haven't broken the bonds, but now the non-bonding pairs on the terminal nitrogen atoms are each aiming at the same location in space. So if the location in space is a metal ion, and my head is this metal ion, then ethylene diamine can coordinate me simultaneously and give me my beautiful Easter hat. I am now chelated. I am simultaneously coordinated by the 2 donor nitrogen atoms from the ethylene diamine molecule, making a ring structure. Every time polydentate coordination takes place, you always make a ring structure. Keep that in mind on bonus quiz number 3. And let's finish by writing this down. Polydentate bond formation interaction is known as chelation which comes from the word chelate. Claw in Greek language. Claw. Ink. I just got clawed by my ethylene diamine chelating ligand. And results in a ring structure. Now, I want to do one more thing. Make my Easter hat again. Put on my Easter hat again. Look at this chelate ring. How many atoms are in this ring? Count them. How many ring atoms? How many? 5. My noggin. Nitrogen, carbon, carbon, nitrogen, and back to my noggin. Keep this count of 5 in your mind. And we'll pick it up from this point tomorrow.